Hello everyone. So here in this video we will learn a complete simulation of a system where we have a permanent magnet, a strong permanent magnet, and it is placed close to a thin plate that is made of iron. Okay, so when the magnet is placed close to the thin plate made of iron, it will get deformed and it will get attracted towards the magnet, because we have a permanent magnet and we have a thin metal sheet. So the amount of deformation and other properties we can study using simulation. So in this tutorial we will learn how to model these systems. So without wasting our time, let's get started. So welcome back to COMSOL Multiphysics. This is the first interface of the software as you launch it. So in this full tutorial you will have a complete simulation workflow, starting from geometry, adding physics and so on up to the post-processing. So this video might be a bit long and I hope that you will watch the full video to get an understanding of how this works. This model is actually an example model, but I thought why not make a step-by-step tutorial so that people who are just starting out can easily follow along and learn how to model. So I always prefer to use the blank model over model wizard. So I will just create a blank model. Blank model is basically creating a new file in any software. So I'll just click on blank model. So when you click on blank model, you will have an interface something like this, where you have a model builder window. Model builder window is basically the details of the file. So you have the file name, global definitions, results. If you add different physics, settings and everything else, you will see in the model builder. So this window is basically the settings window. So whenever you click an option, the settings of this particular option will be shown in the settings tab. And then we have the graphics tab. So here you can visually see the geometry, mesh and results, and also the plots. Similarly, you can have other tabs such as adding physics, adding study and so on. At the bottom you have the message, progress, log, table, maybe if you add probes, the probe data and so on. And at the top, just like Microsoft Office, PowerPoint or any other software, you have different options such as home, geometry, physics, mesh, study, result, develop, etc. Okay, so this is the very quick introduction to the interface. Now the first task is that we will now add the physics in the model. So we click on add physics. The add physics tab is here, but nothing is showing up. Why? Because we have to add a component. So at first we'll go on and click on add component, and then we will add a 3D component. When you add a 3D component, if I go to physics, now you see that all the physics are showing up because we have the physics for the relevant component. Okay, now what we will do, we will now go on to structural mechanics. In the structural mechanics, we'll scroll down and we will go to electromagnetic structural interaction. Now we will actually go on to magnetomechanic interaction, and in the magnetomechanic no current, we will just right click and click on to add to component 1. It might take a few seconds and the physics will be added in the model. You'll see that automatically you will have a moving mesh, solid mechanics and other physics that is added in the model. Okay, so in the study we are interested to study the stationary properties of the system, so we'll add the stationary study in the model. Now the basic structure of the system is ready. Now slowly we can add different parameters in the model and create the geometry. Okay, so in the next section we will add up the parameters in the model to create the geometry. So we'll go on to geometry and we'll click on the geometry tab. Now we are interested to create a work plane. So we'll click on work plane. So in the work plane, we are actually interested to create a quarter of the magnetic geometry. Now in the settings of the work plane, let us locate the plan definition, and we are interested to work in the ZY plane, right? And the X coordinate will shift it to 0.01 and we'll click on build selected. Now we have a plane. As you can see, the direction, this is X, and we have the plane in the ZY. Now inside of work plane, you have a plane geometry. So this is basically the blue region, okay, the two-dimensional blue region where we will draw the two-dimensional geometry. That's why you have a mesh-like structure. So this is basically a 2D plane. Now we are interested to make the geometry. So we'll first draw a circle. So when you click on plane geometry, you have this option. Now let us first add a circle. When you click on circle, you will have the different settings here. So we'll draw a radius of 0.04 and the sector angle to 90 degree. If you click on build selected, you see that you have a circle. So basically you have 1/4 of a circle with radius 0.04 meter. And we are actually interested to change the position along X to a finite offset. So we'll offset this design by 0.06 meter and we'll click on build selected. Now you'll see that the circle gets shifted to 0.06 along the x-axis of this plane. So if I go back to the work plane, so it is along the x-axis of this plane that you have to remember, okay? Otherwise you will make mistakes. So what I mean by that is, in the plane, when you have the xy plane, this is along the x-axis of this plane. Now let us create one more circle. So we'll just right click and click on duplicate. And let us change the radius to 0.02. And again click on build selected. Now we have a circle, something like this. Now we are interested to actually make some Boolean operation in the geometry. So what we will do, we'll go back to the work plane. In the work plane tab, we'll go to Boolean in partition and click on difference. Now in the object to add, we'll select C1. Now in the object to subtract, we'll select C2. Now this is done. Now we will add a rectangle in the model. To do that, in the work plan, click on the rectangle. In the width, type 0.05 and height 0.02. And in the position section, that is along Y, it is offset by 0.02 meter. And you see that we have this rectangle here. Now again we are interested to duplicate this rectangle. So we'll just right click on duplicate to duplicate the rectangle. Now in the settings of this new rectangle, we'll change the width to 0.01 and the position to be 0.05. Okay. And let us click on build selected. Now we have the nice structure. Now let us go back to the geometry, click on build all. So we have this two-dimensional geometry. Now in the workplane 1, we can click on extrude, and in the extrude distance let us type 0.01 and click on build all object. Now you can see we have a nice geometry, three-dimensional geometry. This will be our permanent magnet. Now let us go back to geometry once again and click on a block. Now we are actually interested to set up the dimension of the block. So instead of writing the values directly here, let us use some parameters in the model. So we'll have dm 3 mm. So this is basically the distance to magnet. We have HP, that is 1 mm. This is the plate thickness. Then we have LP, that is 20 centimeter, and that is the plate length. And we have WP, that is 6 centimeter. This is the plate width. And we have H, that is 7 centimeter. This is basically distance to bottom wall. Okay, so now we have the parameters set. Now I'll go back to block 1, and in the width we will write WP by 2, depth LP by 2, and height HP. In the position, we have to change the Z to minus dm plus HP. Do not worry, I will explain everything what is going on. Now we'll click on build all object. So we have this geometry. Okay, so what is happening here is that we have the magnet, we have the plate, and there is a finite separation between the two. So why did we change the Z value? Because if you see that Z is along this direction, so negative direction means that it will have a gap. So this value represents the gap between the magnet and the plate. Okay, so this is almost done. Now in the geometry we'll again add a block. Now in the block we'll change the width to 2 times WP, depth to be LP by 2 plus WP, and height 0.2, and the Z to be minus H. We'll click on the build all, but before that we will add some layers here. So the layer 1 is H minus 2 times dm minus HP, and layer 2 is 2 times dm plus HP, and we'll click on build all object. Now you can see that this is actually a box. So we have a magnet, we have the metal, and we have a air domain. Okay, so the layers are basically making a boundary here. So both sides are empty, and here you have the metal plate. Now if we click here, the transparency tab, you can actually see the layers, the metal plate, and the magnet, right? So our geometry is almost done. So now we will add materials in the model. So to add material, you go on to the materials and we'll click on material tab here, and we'll click on add material. When you click on add material, you should have a tab something like this. You can always drag this, put it in the center so that you can have the material tabs here. Now inside of AC/DC, click on soft iron without loss, right click, click on add to component 1. Now again go to material, inside of AC/DC go on to hard magnetic materials, click on sintered NBFEB grades and click on N35. Just right click, click add to component 1. So we have the two materials that is added in the model. Now let us go on to the materials. In the N35, let us select domain 6. Now we also have to add air material in the model. So we'll go on to add material, click on build in, right click air and click on add to component 1. Now for air, we'll select domain 4, 2 and 1. So we'll clear the soft iron and we'll select the domain for the soft iron, and we'll select this and this. So now we have the magnet, air and the soft iron. So the material selection is almost done. Now let us slowly move on to the physics of the model. Now in the model builder window, let's go on to moving mesh. Let's go on to the deforming domain 1 and let us select domain 2, because we are actually interested to see the deformation in this domain. Now inside of symmetry roller, let us select boundary 4 and 5. Now the symmetry roller is important because generally we use symmetry roller node on flat boundaries of deforming domain, which are also symmetry plane in the model, or where you otherwise want to prevent boundary nodes from moving out of the plane. This allows the mesh to move tangentially to the symmetry roller plane but not in its normal direction. So this is quite important. Now let us set up the solid mechanics settings. Now let us go on to the solid mechanics, and we are actually interested to study the solid mechanics of domain 3. So we'll zoom on and click domain 3 only. Now right click on solid mechanics and click on fix constraint. Now just reposition the model properly and select the 29 boundary. So this is the fixed constraint. Basically this end is clamped virtually. Okay, now we also have to add a symmetry. So again right click, there should be a symmetry here. You have to click on symmetry, or what you can do, you can go on to physics. Inside of physics, go on to boundary and then choose symmetry. So let us add the symmetry planes. Just zoom in and select these two. So now that we have set up the solid mechanics, now the next part is to set up the settings for magnetic field, no current, that is the MFNC. Now just go on to the magnetic flux conservation, and here choose the BH curve, the magnetization model to BH curve. Now we have to add a magnetic flux conservation. So we'll go on to physics, then inside of domain we'll add magnetic flux conservation. So we'll select the domain 6 for the magnetic flux conservation, and in the material type we'll choose solid, and inside the constitutive relation BH in the magnetization model choose the remnant flux density, and here set up the value of E vector, that is 0, 0 and 1. Now again we'll go on to domain, click on magnetic flux conservation, and now we have to select domain 4, 2 and 1, basically the magnetic flux conservation for air. Okay, now we have to add a symmetry plane, so we'll go on to boundary and click on symmetry plane. Now let us select the symmetry plane 1. So we'll select one by one of all the faces that is pointing on this side. So we have 1, 4, 7, 11, 14, and then we have 17, 20 and 23. Okay, so this is fine. Now we have the symmetry plane 1. Now again we have to create another symmetry plane for the other side. So we'll go on, click on symmetry plane 2, and in the symmetry plane 2 we'll do the similar thing, that is we are going to select all the planes in the model that is pointing along the minus y axis. Okay, so here we have 2, 5, 8, 12 and 15. So our physics is almost done. So now we'll go to materials, click on soft iron, and we are interested to see the settings for the soft iron. So inside of material contents you have the different settings here. So in the Young's modulus, let us type 200 GPa and Poisson ratio 0.29 and density 7870 kg per meter cube. Something is wrong, so this is 7870. We have kg per meter cube. I hope this is fine. Yeah, so we have the details for soft iron. So we are going to the home bar and we will add a parameter. So we have a second set of parameter. In the second set of parameter, let us write the new variables here, that is AP. This is the accuracy parameter, and then we have Hmax1. This is 5 mm to 2.6 mm times AP. So this is the meshing parameter. Similarly, we have Hmax2. I'll just copy this expression and I'll just copy and I'll paste, and I'll change the values to 20 and this to be 10, and this is again the meshing parameter. Okay, so this is done. Now we are going to create the mesh and set up the mesh elements. So why we are doing all this? This is because we need to create the mesh carefully in this domain to accurately measure the phenomena and deformation that will be happening due to the magnetic field. So now we will go to mesh. I'll go to mesh, and in the boundary let us choose a free triangle. Now in the settings of free triangle, so we are actually interested to select the surfaces that will be interacting with each other. So here I'll just click the transparency, and it is actually difficult to actually choose the surface here, but I will try my best. One thing that can be done is that I can actually hide the surface, right? So if I click and hide and select the surface here, yeah, now I can actually see the surface. So if I select this surface and the surface of the magnet, so these are the two surfaces that I need to select to create the free triangle. And I'll just reset the hiding. I don't want to hide everything here. Now one more setting that is needed to be done for a free triangle is that I'll just right click on size. Now in the element size, let us choose custom, and in the maximum element size, let us set up to hmax1 that we have set up in the parameter. Now in the mesh, click on swept, in the domain selection region, click on domain, and here you can click on the paste selection and type 5 to 7 if you are following the same model, and you will see that the selection of the domain will be done. Basically the magnet will be selected. Now in the swept, right click on distribution, select 7 and click on remove. So here in the distribution, type 10. Now again, right click on swept one, click on distribution. Now we are interested to select domain 7 and we'll click on 2, that is the distribution to 2. Now in the mesh, we'll again create a swept mesh, and here we'll choose the domain, and we are actually interested to select the domain 2 here. Okay, so this is domain 2. So we'll again go on to mesh 1 and create a swept mesh, and we will select the domain here, and we will manually select the domain 3. Now we'll right click and click on distribution, and here we'll select the number of element to 3. So we are almost done to create the mesh. Now again we'll go on to mesh 1 and click on free tetrahedral. In the free tetrahedral, right click to add a size settings. Now we'll choose custom and we'll set up the maximum element size to hmax 2. Now our settings are almost done, so we'll click on build all to build the mesh of the model. As you can see, the mesh is quite efficient and we don't have any unnecessary mesh here and there. Only at the end of the metal plate there is a dense mesh, otherwise the mesh is quite nice. This is because these settings are from the default COMSOL model. That's why it looks so perfect. Otherwise, if you are working on a new model, it might take some time to actually get the optimum value of the mesh. So now that you have set up the physics and the mesh, the final part is to set up the study of the model. So the first step is to add a parametric sweep in the model. So we'll go on to study, click on parametric sweep, and in the settings click on the add button, and here in the drop down list we will select DM and we can write the values that we need to sweep. So let's say we want to sweep 7, 5, 4, 3, or maybe 7, 6, 5, 4, 3. Okay, and the parameter value is in millimeter. So this is the basic settings for a parametric sweep. Now in the study toolbar, click on show default plots. Now in the parametric sweep, if you go on to the output while solving section, we want to plot the plot group, the different plot group we have. So the default is set to stress solid. Now our settings are almost done and we are ready to visualize our model. Hello, so we are back. So I made a small mistake here. In the symmetry plane, there are two symmetry planes and both are 90 degrees to each other, right? So at the symmetry plane, the physics is basically n dot h equal to 0, and on the other it should be n cross h equal to 0, right? Because both are in the other direction. So the symmetry plane 2, we need to set it to antisymmetric. And then so now I will click on compute and check the results. So the simulation is done and we have our results. So now we need to make some changes in the dataset to actually visually see the results. So we are actually exploiting the feature for the symmetry in the model to actually visualize our results. So in the dataset, what we will do, we will go on to the dataset and we will now go on to results. In the results, go on to more dataset. Inside of more dataset, you have to choose mirror. Now click on mirror 3D. Now as the term suggests, it basically mirrors the solution across a plane. You can either have a quick plane or a general plane. So for now we are actually interested for a quick plane. Symmetry along YZ plane. Now we'll change the dataset to parametric solution and then we'll click on plot. So as you can see that we have a dataset that is actually mirror across the YZ plane, right? So we'll rename this to YZ plane. Similarly, we'll again go to results, more dataset, mirror 3D, and then in the dataset we will select the mirror YZ plane and choose the XZ plane, and we'll click on plot. So now what actually happened is that we solved the one section of the model, we mirrored the solution, so this is the YZ plane, and the whole plane we mirrored across the XZ plane. So then we have the 4 sections, okay, and it looks like a complete solution of a full 3D salt magnet without actually compromising the computational cost. So we'll rename this to the XZ plane. Now let us calculate the dataset for another XZ plane. So we'll just duplicate this, and now this will be anti-symmetric, okay. And what we will do, we'll go on to the advance, we'll click on the define variable, and in the vector transformation we'll select anti-symmetric and we'll click on plot. So we won't visually see this change because here the plot is basically the volume of the data that is being saved in the dataset. Now in the parametric solution, the frame will choose material. So let us now look at the results for the simulation. So we will first see the default plot of stress. Now in the dataset we are going to select the XZ plane, and in the volume let us select the unit to MPa, and we'll click on plot, and now we have this nice plot, and you can already see the deformation that is happening in the model. Now to visually understand better the deformation, we'll right click the volume 1 and we'll select deformation. Now here these are the different components, and we have the scale. So we'll choose the scale to 2 to actually or let's say 1.3 to actually see the deformation change. As you can see here, the metal plate has bent towards the magnet. So now let us go to the magnetic flux density norm. We have a plot something like this, so I'll click here. Now in the dataset we'll choose the XZ antisymmetric. I will click on plot, and we see that we have a plot something like this, but the plane is shifted along X. So let me see in the multi slice here, the X plane, let us type 0 and click on plot. Yeah, so now the plane is at the center, and there is a problem with the Z plane also. So Z plane will type minus dm and click on plot. Similarly, the Y plane, it's fine, we can leave the Y plane as it is, or let us set the Y plane to 0 also. So now I hope that the planes will be at the center cutting each other, or if we don't want, we can actually remove the Y plane so that we can have this structure. So we will make a 3D plot again to actually calculate the displacement magnitude. So we'll just duplicate the stress solid and we will write this as displacement solid. I'm just following the default model that is provided by COMSOL to actually make this, so I'm not discovering anything new. That's why I'm trying to follow as it is. Now we'll go to the volume and in the expression click on insert expression, and here you can write solid dot displacement, and in the unit instead of meter we can select millimeter. You can click on plot. You can see that it is a nice plot and it shows basically the color represent the displacement. So you can always change the color to thermal to actually see the change. So higher the lighter color, higher is the displacement, right? So now we'll go to definition and we'll go to non-local coupling and we'll choose maximum, and we'll choose domain 3, that is the metal plate in the maximum. So now we are also interested to calculate the force calculation for post-processing. So inside of the physics, we'll click on the domain and we'll click on force calculation and we'll select 3. If it is difficult to select 3, we can type 3 and click on OK, and we'll keep the settings unchanged. So now we'll go to the study and click on update solution. We can check the progress. It might take few seconds to update the solution, and the solution is updated. Now let us go on to result. So in the home we'll click on add plot group, or we can go on to result and click on 1D plot group. So here we can write this as displacement. We'll choose the dataset to parametric solutions, and we will right click on the global solution, and in the global solutions, since if you remember we calculated the maximum displacement, so what we will do, we'll go here and in the expression we will just paste this, and in the bracket we'll write W by dm and the unit in percentage, and here we will write maximum T by W by dm. So we'll click on plot, and we have this plot here. Now you can always change the levels. So we have the maximum displacement in percentage from the distance from the magnet. So when the distance to the magnet is small, the displacement is high, as you would expect. And of course you can change the style and the style of the line. So in the width, let us change to some higher thickness. So this is basically the displacement graph. Now we'll also calculate the total force. So we'll go again to result, click on 1D plot group, we'll write the force, and we'll again create a global variable. So here in the expression we'll type force, and you'll see that you should have a force along the z-axis. And since the total force will be 4 times, so we solved only 1/4 of the model, so this will be 4 times that, and we'll click on plot. So we have a point in the force. We'll again choose the parametric solution and click on plot again, and now you see the force with respect to the distance from the magnet. We can change the thickness of the lines. so that we can visually see the force. So we are pretty much done, and we have the different plots. So we'll go back once again. At first, what we did, we added the physics. So we had this 4 physics here. Then we created the geometry of a magnet, a metal plate surrounded by air. We set up the very basic physics. We changed the material properties. We created the mesh smartly using the parameters so that we have the minimum number of mesh element and we get quite accurate and close results. To do that, we set up the free triangle, and we also set up the shift mesh and the free tetrahedral along with the different size settings of the mesh. Okay, and also we set up the maximum and minimum size of the element so that the solution converges properly. And after that, we set up the parametric sweep and solve the model. We got the result, but to make the result more realistic, we mirrored the solution across the 2 sides, and we set up the antisymmetric property due to the effect of the magnetic field here. So here you have to remember that you have to choose antisymmetric if you are making a symmetry on the other side. And then we actually plotted the result, calculated the displacement and the force, and finally we are done. I hope that you learned how to model this kind of simulation in COMSOL Multiphysics. And if you like my effort to create these videos, do subscribe to this channel and also give a like. It helps me to keep my motivation to create more quality tutorials for you all. Thank you for watching and have a nice day ahead. Hello everyone and welcome back. We are here with another interesting tutorial on heat. This is the first tutorial on heat, and I got a lot of requests regarding phase change, so I thought why not make a nice tutorial using water. So as you can see in this animation, ice is being converted into water. So this is the hypothetical shape of a rectangle where heat is provided on the right hand side, and you can see that ice is being converted into water, and we have animated with time. So let us first go through the equation and theory, and then we'll move on to the software and learn how to model phase change in the software. So to derive the phase change equation, we begin with the basic heat conduction equation, also known as Fourier's law. So you might know that Q is equal to minus K times delta T. So Q is the heat flux, K is the thermal conductivity, and delta T is the temperature gradient. Now let's say for a volume element, the rate of change of internal energy due to heat conduction is given by rho Cp del T by del T, where capital T is temperature and small t is time, is equal to del K del T. Okay, here rho is the density, Cp is the specific heat, T is the temperature, and small t is the time. During a phase change, the material absorbs or releases latent heat without a change in temperature. This is modeled by adding a term representing the rate of energy change due to phase transformation, and it is represented as rho L del phi by del T, where L is the latent heat of phase change and phi represents the phase fraction. Now if we write the complete phase change equation, it looks something like this. So we have rho Cp del T by dt is equal to del dot K del T plus Q, that is the heat, minus rho L del phi by del T. Here Q is the internal heat generation per unit volume. This equation accounts for the heat conduction, internal heat generation, and the energy involved in the phase change. So you can say that this is the complete equation for phase change. So for example, let's say an ice cube is converted into a glass of water, then basically we apply this equation to get the time taken and the different heat exchanges occurring between the two phase change. So before we jump to the software and start modeling the water ice system, let us first understand the phase diagram of water. It is quite interesting, and let us see what we can understand from this. So we have pressure on the one side and temperature on the other. Now this is called the triple point of water. This is the most interesting point, that is around 0 degrees Celsius, right? Now as we increase the temperature, you can see that the water tends to form the water vapor, and as you try to cool, it either forms water, and as you cool further, it goes towards the ice region. And at a pressure below a certain limit, there is no ice. Even if you lower the temperature, it only forms the water vapor. So this is quite a good diagram to understand the different phases of water in terms of pressure and temperature. Now let us see a different graph where we plot the temperature, and here you can say time. So what is happening here? Let's say we have a glass of water. Basically you can think of it as ice initially, and we are providing some heat, and we are actually trying to measure the temperature with respect to time. So what is happening here? At first the ice is at minus 20 degrees Celsius, then as we are heating it up, the temperature will rise, and at 0 degrees Celsius ice will form water. There will be a phase change. Since there is a phase change, you can see that the temperature will not rise. All the heat will be absorbed, and it will be used in the latent heat of fusion that will actually convert ice to water. And then the temperature of water will rise with temperature again at 100 degrees Celsius at room temperature and pressure. It will again form water to water vapor. So this is again a latent heat is being used to convert it into vapor. So this is how it works. That is why the graph actually looks something like this. So these flat region are actually due to the latent heat. So now what we will be doing is that we will first take a rectangular block of ice. Okay, so this is ice, and what we will do, we will provide heat on one side that will basically melts the ice, and we will define the density, the specific heat, the latent heat, and time, and of course the dimension of the ice, and we will try to figure it out with time, how it is melting, what is the temperature profile, heat profile, and so on. Okay, so this is the main objective of our work, and in the meantime we'll also set this as an insulator on the other three sides, so that we do not consider the radiation and the other phenomena that are involved in realistic scenarios. So this is how the modeling workflow will begin. So let us jump into COMSOL Multiphysics and see how we can solve this problem. And of course, if you are interested to get a Python version of this modeling, This can also be done. Do comment in the description if you are interested, then I will create a fully Python tutorial of a two-dimensional phase change of liquid, totally in Python. So let's jump into COMSOL Multiphysics and see how we can do this modeling workflow. So we are in the COMSOL Multiphysics window. What we will do first is we'll create a blank document, and then we'll create a 2D component because we're interested to study a rectangular shaped ice. So we'll go on and click on blank model, and we'll just click on add component and then click on 2D component. It might take few seconds and we'll have the window. So what we will do, we'll first draw a rectangle and then we'll add different settings. So we'll go on to geometry and then we'll click on rectangle. In the width, I'll just write 0.01 and height 0.001, and I'll click on build selected. So you can see that we have the block ready. Now we'll go on to the parameter and just add different values that will be needed in our workflow. At first we'll add the transition temperature. So we'll write T trans and this is 0. Okay. So we are writing in Celsius. So what we can do, we can just write as DEGC. Okay, that means that this is in degree Celsius and the value will be converted into Kelvin. And now we will add the lower temperature. So T0, and this is minus 10 degree. Okay, and let us set the temperature of the hottest side, basically the region where we are actually providing the heat. So let this be 85 degree Celsius. So all this temperature are done all together. Now let us write the density of ice and water that will be needed. So density of ice is 918, and of course we should write the unit. So this is kg per meter cube. I'll just copy this, and density of water is 997, or let us take 1000 for simplicity. Of course you can change the value in your modeling workflow, that doesn't matter. And then we'll also write the ratio of water. So that is the ratio of the ice and water. So I'll just copy and I'll divide and click on paste. Okay, so this is the ratio of densities. So we are done with the basic parameter. Now what we will do, we will add the material, and then we can add the module in the physics, add the mesh, and then model. Okay, so we'll add a blank material. So this will be ice, and we'll again add a blank material. This time this will be water. Okay, don't worry, we'll fill in the details later, but for now I'll just select this. And what we will do now is that we'll add the physics interface. So we'll go on to physics click on Add Physics. In the Add Physics, we are interested to study the heat. So we'll go to Heat Transfer and Heat Transfer in Fluids because we will be studying water. So I'll click on Add to Component 1. It might take few seconds, but that component will be added here just before the mesh. So you can wait few seconds. So the heat transfer in fluid is added. So I can close the physics because I don't need it now. And as you can see, the physics has already selected the block. Now I'll go back to water and you can see that it is asking for these three properties, that is the thermal conductivity, the density and the heat capacity. So let us write the values one by one. So what is the thermal conductivity? The thermal conductivity is 0.613 that I got somewhere from the tutorial. What by M into K times the ratio. I'll just copy this. So I'll copy and I'll just paste it. What is the error I'm getting? Unknown variable ratio. Oh, I think this is fine now. Probably, yeah. So heat capacity at constant pressure. What is the value of Cp of water? So the heat capacity of water is 4179 in SI unit. Okay, and density. So the density of water is the density of water times the ratio. Why am I not writing only density of water? Because remember that there will be a phase change and the density of water will not be fixed. If we consider the total volume, the total density will not remain fixed. It will change with time because the percentage of water will increase and the percentage of ice will decrease and so on. So we are done with the water and now we are interested to write the properties of ice as well. So I'll just disable the water for now. Now I'll just move this. So as you can see, for ice also we need the thermal conductivity, density as well as the heat capacity. So the heat capacity of ice is 2052. The density is density ice and the thermal conductivity. So the thermal conductivity is around 2.3. So here we are writing the density of ice because initially the density of ice is the density of the whole block. Okay, so we are actually done. Now what we have to do is we need to set up the physics. So click on the heat transfer for fluid. In the fluid 1 section, right click and click on phase change material. When you click on phase change material, a lot of different settings will pop up and we need to actually fill in the values. So the phase change between phase 1 and phase 2, the temperature is at 0 degrees Celsius. So this is fine because the phase change between ice and water is at 0 degrees Celsius. So we don't have to change this. Now the transition interval between phase 1 and phase 2. What is the value of delta T? So for simplicity, let us take this as 1 Kelvin. Okay. And the latent heat from phase 1 to 2, that means the latent heat of fusion. So we need to write the latent heat of fusion. So I think it is 333. It's probably 333 if I am not wrong. So I won't change this. Now in the phase 1, we have to select as ice. Remember that the phase change is from ice to water and not the other way around. And the second is water. And the rest of the parameter values it will automatically take from the material component. So you can see that the density and other details are here already, that will automatically be taken from the material. So we have almost set up the phase change. Now let us click on the initial value. So what is the initial value of the temperature? Is it 0 degrees Celsius? No, we have already set up the initial value, so that is T_0. Remember that this was our initial temperature, that is the value of temperature of ice. Now we need to add the thermal insulator. By default you will see that the insulator will be added, so we don't have to worry about that. And we have to add the temperature, so I'll click on temperature. So here's the interesting part. We will create a step function and the temperature profile will be in the form of the step. So what we'll do, we'll go on to global definition. In the function we'll click on step, and here we'll write T input, and here we will write T_0 to, I'll just copy this because I generally don't remember the value names. So let us see how the plot actually looks. It looks something like this. So I think this is fine, but we can of course set the location. So we can set it to 0.04. Yeah, this is fine. So we have set up the temperature ramp. Okay, so here what we can do, we can call the function T input, and we can actually set up the temperature. So we'll just paste, and within brackets we can write T, that is the time by default in COMSOL Multiphysics, and to stay consistent with the unit we will write 1/s. Okay, so this is the format you generally use to write the time dependence and also to keep consistency with the unit. So we are almost done. Now let us create the mesh. To create the mesh, what we need to do, we just click on first build all and see if it is working fine. But I am not actually happy with the default mesh, so I'll just go on to mesh, click on distribution, but yeah, I'll just click on user control and I'll just click on distribution. I'll select these two sides, maybe I will add 50 elements, and I will just duplicate this distribution, click this, and maybe I'll just add 16 elements here. Then free triangular, I'll keep the remaining, and maybe I can add a distribution here. Let's see. Yeah, so the mesh is almost done. So I tried to add a finer mesh here because there will be a temperature gradient towards the end. So we are almost done. Now the next part is to set up the study. So we'll go on to study, click on add study, and we are interested in a time dependent study. So we'll just right click, click on add study. Again, it might take few seconds if your system is a bit slow. Don't worry. So in the time there will be nothing in 1 second. So if you think physically, let's say you have an ice cube, how long does it take to melt? It generally melts in 30 seconds to maybe 1 hour or few minutes. So we'll first set the range from 0 to 20 or 0 to 10 to 50, and then we'll set a range from 60 to 20 to 120, and then another range from 120 to 60 to 1100. Okay, and I'll just change this to 100 to keep it consistent. So I think the values are not overlapping. I hope this is fine. So maybe I can change this to 1300 or a multiple of 60. So 1200 is fine, I guess. Let's see. And in tolerance, we'll just set it to 0.01 and we'll click on compute. So let's wait for the result. So the simulation is done and you can see that the temperature gradient is shown here. Now I'll go on to 10 seconds. I'll first go on to 0 and click on plot. So you can see initially it is all ice. So 263 Kelvin is basically minus 10 degrees Celsius. So I'll go on to surface and instead of Kelvin I can just select degree C, click on plot. Now you can see that the plot is in Celsius, so it is minus 10. Now if I go on to higher temperature, let's say 10 seconds, you can see that the temperature is actually rising. So this end is around 85 degrees Celsius as we have set it to 85, right? And the colder region is around minus 10. And after each time you see that the temperature is actually increasing and basically the ice is melting. So if I click on 420, you can see that all the ice has melted. Why? Because the temperature gradient you can see is close to 30. That means it has already melted into water. So if I click on 360, it has melted 300. So probably after 300 seconds, all the ice has melted. It is something like that. Okay, so now what we can do, we can actually add another study and then simulate it to get the result without the latent heat, and then we'll compare the results. So I'll go on to add study. We'll again add a time dependent study. To save time, I will just copy the range, paste it here, and I will just add the sweep, add the latent heat. So I haven't set the latent heat here. What I can do is I'll go on to the physics, and here what I can do, I can just cut latent ice, okay, and here I will create and I'll paste the value. Okay, now I think this is fine. Yeah, so I'll go back here, I will choose the latent ice and set it to 0. So basically I am not considering any latent heat of fusion in this case in study 2. So here I'll just write no L. Okay, and now I will click on compute and see the results. So I'll just wait for the results. Probably this will take less time because it will now not have the latent heat calculation. So this is the temperature profile. Now in the two-dimensional plot you won't see much of a difference. The difference will be prominent when we will plot the one-dimensional graph. So I'll go on to result, click on 1D plot group, and then we'll click on line graph. Now I'll click on define cut line and we will just set 2 points just to check the result, and the temperature will select degree Celsius and click on plot. So we can select solution 1, define the cut line once again. So we can select this and click on plot. So this is with latent heat. So let me just plot this once again. I'll just duplicate this, and this time I'll select the second solution, and again I will choose the points and click on plot. So let us first see the graph with latent heat and try to understand what is going on. Now you can see that at lower time, that is at 0 second, all of them is at minus 10 degrees Celsius. Now at some higher time, some of the ice has melted, and at 0 degrees Celsius you can see it is getting flatter because of latent heat of fusion. So it is suddenly changing. The curve is having a sharp pointy edge here. You can see why? Because the water and ice interface, the temperature is actually 0 degrees Celsius because ice is melting it into water without actually increasing the temperature. Now if you look at this graph without the latent heat, you can see that the curve is actually smooth. Why? Because here in this case the latent heat of fusion is not there, it is 0. That means it has nothing to resist the change in temperature. So the ice will easily get converted into water. So at higher temperature it will gradually convert it into lower temperature without any sharp change at 0 degrees Celsius. Don't worry about these discrepancies. It generally arises if the mesh is not finer and so on. But if we just look at these two graphs, you can see that clearly there is a visual difference between the graph using latent heat and the graph without using the latent heat. So this is the main inference of this work, and of course you can do various other studies, other plots, two-dimensional plot, time-dependent plot, and so on. So my goal was to show you how you can actually model the phase change. Now depending on the type of study you are doing, of course you have to use different equation, different model, as well as different equation. It may not be as simple as water and ice. Of course it has let's say if it has some other liquid mixed with water, then the process will be slightly different. And if it has some temperature dependence property, then of course you have to implement it, and so on. So I hope you learned something from this video. Hello everyone and welcome back. Hope you are doing good. In this video we will learn how you can model permanent magnet in COMSOL Multiphysics. Here we will have a complete tutorial starting from creating the geometry, adding physics, running the model, and we'll have a complete workflow so that you can model permanent magnet in the software. So to start, we will first model a bar magnet. So we know from the magnetic properties in a bar magnet, we have two poles, that is the north and the south, and the field line actually travels from north to south, something like this, right? So this we will try to model in COMSOL Multiphysics. We'll first do that in 2D, and then if it works, we will extend that in 3D in real life situation. Okay, so without wasting any time, let's jump into the software and start learning. We'll start with a 2D model first, and then we'll move to 3D. So we are in COMSOL Multiphysics. This is the new interface, and we'll start with a blank model. So we'll click on blank model here. You can always click model wizard and select the physics interface and so on, but I always prefer to create a blank model and then these settings later. So I'll click on blank model. When you click on blank model, you will have an interface something like this, and here the first step is to add a 2D component. What is a 2D component? It is basically a two-dimensional physics interface in the software. So to do that, you go on to home, click on add component, and click on 2D component. When you click on 2D component, a 2D component will be added in the model builder. You can see that. So this is basically the 2D component, and here we will slowly add up different details for the simulation. So before we start, let me just briefly explain about the component section. So basically, a model component is a fundamental part of the model that contains a geometry with its associated physics interface. Okay, and it also includes the mesh, the variables, and other definitions that are local to that component. So whatever definition you create here, for example a variable, it will be within this component. Okay, these are not global, these are local variables. And the component node defines the namespace for each part of the model that is defined in a model component. A model can have several component node. So for example, this is a 2D node. You can create a 3D component and so on, and then you can interlink the different physics and so on. Okay, so let's say you have a complicated model, you want to solve the two-dimensional part in a particular component, that you can do, and then you can create a three-dimensional version of the 2D component that also you can do in the same model itself. So this is quite useful, but in this tutorial we won't go into those details, so we'll just work with the 2D model. So let's begin. So at first we'll go on to geometry, and then we'll create a bar magnet. Okay, at first we'll change this to centimeter, because in general for realistic system we generally work with bar magnet that is like, let's say 2 centimeter or 3 centimeter and so on. So we'll go on to geometry. Better we'll go on to sketch and just draw a rectangle. To do that, we can just drag a rectangle here, and if we go to geometry and click on sketch again, we have a nice rectangle. So this will act as the bar magnet in our model. Okay, now we can always draw a circle that will act like the air around it. Okay, so in finite element simulation, it is better to also draw the surrounding area, because we are going to solve the equation around the magnet. So we'll draw the surrounding. So we'll draw a circle. To do that, go on to sketch, click on circle, click on the center and just drag. You will have a circle. Okay, and again, if I go on to geometry, click on sketch, click on build all object, and click on zoom extents, we have the magnet and the air. Okay, so this is the basic geometry that we are going to work. So now that we have created the geometry, we will add the physics in the model. Okay, so we'll go on to add physics, we'll go on to AC/DC, and here we'll go on to electromagnetic fields, click on magnetic field, right click, click on add to component. Now the magnetic field interface will be added in the 2 domain. Now let us add some material in the model. To do that, click on material. You can go on to material here, click on add material. When you click on add material, you should have a material tab somewhere in the window. Click on add material. Here go on to AC/DC. You can click on magnetic materials. I'll just select any one of the magnetic material here because this is just for demonstration. Depending on the type of project you are working, you might select your own material and work. And we'll add a blank material. So this will be air. For air, I'll select this domain, and for the magnet, I'll select the magnet. Okay, so I'll just remove this. So we have 2 material, one air and one magnet. For air, it is asking for 3 different values, that is electrical conductivity. So we know that the electrical conductivity of air is 0, and let's say relative permittivity 1 and permeability 1. Okay, so this is done. Now we need to define the magnet in the model. To do that, you go on to magnetic field, you can go on to the physics. In the domain, click on magnet and select the magnet in the domain selection. Okay, and here you will see that you should have 2 options, that is north and south. If you're using version 6 or above, if you select magnet, you automatically have 2 different options, that is north and south. So just click on north and we'll select this to be the north pole, and for south I'll click here this to be the south pole. Okay, so we have defined a magnet of this domain where the north pole is this line and the south pole is this line. Okay, so the physics interface is almost done. The next step is to add the mesh in the model. So we'll go on to mesh and click on add mesh. So for time being, I'll just delete this older mesh. So I'll just rename this mesh 1 so that there is no confusion. So now I'll click on build all. Okay, you can see that the mesh is not that great because it is quite coarse. So what we'll do, we'll manually mesh the model. So in the sizing, or I'll just create free triangular, and here I'll just click on size. Okay, and in the geometry selection, click on domain and select the magnet, and here in the element size, click on custom and check the maximum element size. I'll just select 0.05 centimeter and minimum to be 0.01, and the element growth to be 1.2, and I'll click on build all object. Now you can see that the mesh density of the bar magnet or the permanent magnet is quite dense, and then you have the air domain. So the mesh actually looks pretty nice, and I think this would work for our model. So we have the geometry, we created the material, we added the physics, we created the mesh. The last step is to add the study. To do that, go on to study, click on add study. If you have already clicked on add study, it should have the add study tab somewhere here, and here just select on stationary, right click, click on add study, and you should have the study added in the model. Since this is a simple model, there is not much settings to change. If we have done the proper settings, we can just run the model and see if it works. So I'll just click on compute and we'll wait a few seconds. If there is any error, it should pop up. So we have our results here. So we have this beautiful plot that is generated by default. So this is the bar magnet, this is the air domain, and you can see the magnetic field line that is coming out from the north pole and ending in the south, as you would expect in a bar magnet. If I zoom in, you can see the lines as well. So I'll click on zoom extents. To better understand the magnetic field line, you can go on to the streamline plot, and here click on interactive arrows. What interactive arrows does is that you can animate the field line along the arrow points and see how it behaves. So if I slowly move the cursor along the local time, you can see that the arrow actually moves from the north pole and then it ends in the south pole, right? So this is how you actually model the magnetic field in COMSOL in 2 dimension. Even in 3 dimension, it is quite similar. We'll do that probably in next video. But let us do one thing. Let us actually study the magnitude of the magnetic field in the model here. Okay, so we'll go on to result. We'll click on 1D plot group, and in the 1D plot group we'll click on the line graph, and here we'll define a cut line. Let it be through the center of the magnet. Okay, and we are trying to measure the magnetic field in Tesla. So we'll click on plot. So you can see that as soon as we get closer to the magnet, there is an increase in the magnetic field, and inside the magnetic field is quite high, it is obvious, and then it is symmetric along the other side. So if I go on to the 2-dimension plot, you can see that the magnetic field will slowly increase here, and it will be maximum, that is 1.1 Tesla inside, and then we will have a symmetric texture on the other side. So let us select some other point. So we'll go on to define cut line. We'll select the first point maybe somewhere here, and the second point somewhere here. So now what we have selected is that we have selected the magnetic field along the air domain, so it is not crossing through the magnet, and we are interested to see the magnetic field along this line. So personally, I would expect that the magnetic field should increase, and it should be maximum somewhere here, and then again it should decrease, and it should be a symmetric plot as well. So probably it will be maximum or minimum at the center, because all the fields are concentrated along this point. So let's see what happens. So I'll click on plot. Yeah, so when I click on plot, you can see that the magnetic field is actually increasing at the center, and then it is decreasing. So if I go on to the 2D plot, you can see that the magnetic field is actually highest at the center, and then it is decreasing. So logically also you can see that the results are quite aligned with the logical understanding of magnets. So this is how actually you model permanent magnet in COMSOL Multiphysics in 2 dimension. In the next lesson, I'll just model the permanent magnet in 3 dimension. It is slightly difficult than 2 dimension, so I think it's better to make a separate video of it, and then probably I'll try to model the horseshoe permanent magnet in COMSOL Multiphysics. And yeah, that's it. If you learned something, please do like this video. Majority of you are not subscribed to this channel as well, so it is my request, if you are enjoying this video, do give a like and subscribe this channel. That is the only way I get motivation to create more videos. And as you can see, these high quality videos takes a lot of effort to actually work and render, in spite of being in a busy schedule in the research work. So I would appreciate if you show some love in these videos. Thanks for watching, and have a nice day ahead.